Good afternoon and welcome to the Idahoan Show. Today I want to talk about height over bore, or HOB as it is commonly abbreviated, and which I facetiously refer to as the Hobgoblin, because it can be a very significant and frustrating problem that is all too often ignored in the shooting community. And what I mean by height over bore is the distance above the barrel that your sights are mounted. So if you've got a scoped rifle, this would be the distance from the axis of the barrel to the axis of the scope. And the reason that this is significant is that it determines how far above or below your line of sight the point of impact of the bullet is going to be, especially at close range. And to make sure we understand exactly what's going on here, let's have a seat and see if we can develop a mathematical model to relate point of impact to height over bore. Okay, so if we draw this up in Cartesian coordinates, we'll let our line of sight be the x-axis. X will be the distance downrange from the muzzle of the gun, and then the Y dimension will be the distance above or below our line of sight where the bullet impacts a target at that distance. I'm going to model the bullet trajectory as a parabolic arc. I realize, of course, that with air resistance it's not going to be a perfect parabola, but hopefully this approximation will be good enough for practical purposes. So then we've got the generic equation of a parabola here, and we can start to find these coefficients based on what we know about this situation. For starters, at range equals 0, these two terms are going to drop off and we'll just get y equals c. So c is going to have to be equal to negative height over bore, the distance that the barrel is below the line of sight. Then we know from Newtonian mechanics that for this to be a parabolic trajectory, this a term is going to have to be equal to negative g over v squared, where g is the acceleration of gravity and v is the horizontal velocity of the bullet as it moves downrange. Now, again, as a first approximation, I'm just going to take v as the muzzle velocity that I would measure with a chronograph. We know that because of air resistance, velocity will actually decrease as the bullet moves downrange, so it's not going to be quite constant over this distance. As well as the bullet also has a vertical component to its velocity because it is going up and then down, but in most practical cases that vertical component is going to be pretty negligible compared to the speed of the bullet moving downrange. And finally, we know that at the distance where we zeroed our optics, the parabolic trajectory of the bullet and the line of sight are going to intersect. So if we take that and plug that plus our known coefficients back into this generic equation, we can solve for our final coefficient b. And if we do that, this is what I get. This equation gives us a mathematical model to predict the point of impact of the bullet relative to the line of sight as the bullet moves downrange in terms of the acceleration of gravity, the distance at which the optic was zeroed, the velocity of the bullet, and the height over the bore at which the optic was mounted. Now that's all well and good, but how accurately does our mathematical model reflect reality? To determine that, we need to go out to the range and put it to the test. And again, I'm going to test it mostly at relatively close range, both because close range is where height over bore becomes significant, and that's what we're investigating, and because the simplifying assumptions that I've made, like neglecting air resistance, are likely to be okay at close range, but at longer distances, air resistance becomes more of a significant factor. So to begin with, let's test it with this AR-15. Now, from previous testing, I know that this gun shoots about 1.5 inches high at 100 yards, and I've got data on point of impact from there out to 500, but What I really need here is the close range data, so we'll test this out to 50. Looks like our height over bore in this case, I'm going to say is just shy of 2.5 inches, like 2.4, maybe 2 3/8. And that's really about as low as I can mount a scope on a gun like this and still be able to see through it. You know, AR-15s are really kind of difficult to mount the scope very low to the bore. $28.91, $29.80, $29.12. So looking at this target, my point of aim or line of sight, of course, is the center. And so we can measure out at 1 yard, our point of impact is about 2 5/8 inches low. And then as we move further away, that gradually walks up to being just about a 1/2 inch low at 50 yards on average. Here's how our model compares for the 223. The blue line are the predictions of the model. The red dots are our actual data points from testing with the 223, and then this dotted red line is a best fit parabolic curve that's been fit to our data points. Honestly, these data points deviate more than I was expecting from a nice parabolic curve. Now, that could just be scatter in the data. Maybe if I fired a 100-shot group at each of these ranges, so that we could average out all of the scatter, they would conform to a nice parabolic relationship. But I certainly don't have the time or the ammunition to do something like that. And honestly, I would not expect to have a very large group if I'm only shooting at like 10 yards. I mean, I would think I would be putting bullets in the same hole at that distance anyway. So I'm not entirely sure why there's so much deviation there. What I can say is that while the model predicts the behavior in a general sense of having shots low at close range and then eventually passing through the line of sight and being above it at further ranges until it eventually gets back to the 0 point, quantitatively, the model seems to underpredict the amount by which the shots deviate from the line of sight. For example, at 25 yards, the model is predicting that we'd only be like a 1/2 inch low, but our actual data point indicates that we're more than 1.5 inches low. Next gun I want to test is this lever action 44 Magnum. This is going to give us a very different data set because, for one thing, it's got traditional iron sights that are very low to the bore compared with a scope. I'm going to say our height over bore in this case is, between 5/8 and 3/4 of an inch. Meanwhile, compared to the 223, it's a much larger bullet traveling much slower, so it's also going to be a very different trajectory. Okay, with the 44 Magnum, that one was 1691. That one was 1703. That was 1662. Of course, with the 44 Magnum, I used a different style of target so that with the iron sights, I can take a 6 o'clock hold on the upper lobe, and then I'm sighting right there. So this intersection point between the two lobes is going to be our line of sight. And then we can see that here at 1 yard, we're like about 0.8 inches low, and then that walks up to being just slightly high, about maybe 3/8 of an inch high at 50, and then by the time we get out to 100, now we're back down to about 1 5/8 inches low. Here's how the model compares for the 44 Magnum. Once again, the blue line is the model, the red dots are our actual data points from testing, and the dotted red line is a parabolic trend line fit to the data. Once again, the model does not agree with the actual data nearly as well as I was hoping it would. Not only do we have some obvious scatter in the data points, but we can see how at closer ranges, like less than 60 yards, the model is consistently predicting that the point of impact will be higher than it actually is, and then beyond 60 yards, it's consistently predicting that the point of impact will be quite a bit lower. I do notice that if I divide the acceleration of gravity by 3, then the model fits the data a whole lot better. Now, obviously, I'm not operating in 1/3 gravity out here, but it's possible that as I was typing this mathematical model into the spreadsheet, I misplaced a unit conversion, and I am converting from feet to yards and vice versa, which is a factor of 3. So it's not inconceivable to think that there could have been that kind of an error in there. Maybe I can troubleshoot this later, or if anyone else wants to try and independently reproduce my model, that would be great. Okay, so my mathematical model needs work, but I think there's still some useful conclusions that we can draw from our range data. For one thing, we know that at very close range, the point of impact will be below the line of sight by approximately the height over bore. Number 2, that is a non-conservative figure, meaning in testing, we sometimes saw the point of impact at very close range actually a little bit more than what we estimated our height over bore to be. By a non-trivial fraction of an inch. And whether that's just scatter, whether it's a flinch, whether it has something to do with, the optics, is hard to say. What we can say is, if your scope is 3 inches above your rifle, it's possible to shoot more than 3 inches low at close range, by a fraction of an inch. And number 3, qualitatively, I think the model is accurate in the sense of indicating that as range increases from 0 to the distance at which the gun was zeroed, your point of impact is going to rise from being low by approximately the height over bore to eventually passing through the line of sight, being high for a while, and then dropping back to intersect the line of sight at the 0 distance. Now, to put this in practical terms, let's say that you're shooting a scoped rifle with 3+ inches of height over bore at 6-inch diameter circular targets. You start out setting the targets up at 100 yards, and, from an offhand position, you're probably hitting them like 50% of the time. If you can, lie down prone or use a bench rest, then you can probably hit them more consistently. But if you move them up to 50 yards, now, even from an offhand position, you can hit them just about every time with that rifle. Well, then you move them up to like 5 yards. And if you settle the crosshair right dead center on that 6-inch circle, you will miss just about every time. Hopefully this serves to illustrate just how serious of a problem height over bore can be. Going from consistently hitting targets at 50 yards to not being able to hit them hardly at all at very close range. And really, a 6-inch target is pretty big. I mean, if you're hunting rabbits or squirrels or something, the vital area on a small game animal is considerably less than 6 inches across. Same thing if you're in a shooting competition where you have to shoot targets at close range. Or, heaven forbid, you have to use a gun defensively, and in that case, you really want to know exactly where your bullets are going. And height over bore, if it's too great, can make it really difficult to do that. So that's the problem, but what's the solution? What can we do about height over bore? Well, some people will tell you you've just got to train for it. You can fix anything with training. I feel like that's a lousy solution in this case. It's one thing to compensate for bullet drop on a really long shot where you're going to be taking your time and shooting very slowly and methodically. It's a very different thing to think about trying to compensate for bullet trajectory at very close range in potentially a very dynamic situation, whether that's trying to nail a rabbit on the run as you're out hunting small game, or whether it's a competitive shooting match where they've set up some small targets at close range that you have to shoot very quickly. or whether, heaven forbid, you're involved in some sort of dynamic critical incident where you have to defend yourself with a firearm and there are threats located inside of 50 yards, which, if they're close enough to pose a threat, they probably will be at close enough ranges for height over bore to be a real consideration. I mean, sure, if you're just out on the target range practicing, you can try to memorize the trajectory of your gun, including the section of that trajectory from the muzzle out to, 50 yards or wherever height over bore becomes less significant for your particular setup. And then if you're shooting a target at 6.5 yards, you can mentally figure out, okay, at this distance I need to aim 2.78 inches high to nail this target dead center. But if you're in a situation where you're under stress, you're trying to act quickly, you're not going to have time to do those calculations. You're probably going to forget all about that, and you're not going to be able to shoot as intuitively as you need to in that situation. So just trying to train it away is really not a good solution to the height over bore problem. Now, you might also think, well, why don't I just sight in my rifle to shoot dead on at like 5 yards, and then I'll be zeroed for close range. Well, that works as long as your targets are exactly 5 yards away, but from 5 yards to the muzzle, you're still going to have that height over bore spread, and then beyond 5 yards, you're going to be shooting way high. So that's not really a good option either. As I see it, the only way to really slay the height over bore goblin is simply to reduce the height over bore. If you can keep that under an inch such that at close range your point of impact is always going to be within an inch of your point of aim, then it would cease to be an issue. Now, that's really easy to do with something like this, with an AR-15 or other modern guns that we typically put a scope on. It's easier said than done. That said, I think if you're willing to get a little bit creative with the sights that you use and how you mount them on the rifle, there might be some options there, and that might be the subject for a future video. But till then, thank you for watching the Idahoan Show.